Yeah, so our second speaker today is Julia Münch, and she will talk about extending rational Thurston maps. So please, Julia.
Hi, everyone. Yeah, thanks a lot for the invitation. It's an honor to speak here. I will be presenting first some sort of motivation for the result, and then an extension result where we consider rational expanding Thurston maps and extend them to R3 with infinity. And in the end, I will be talking about an application towards Sullivan's dictionary. Also, if you have questions anytime along the talk, please just feel free to interrupt, and I will happily reply. So let's go to first part of the motivation. One motivating question is kind of, if we start off with a holomorphic function on the Riemann sphere that we will view as the unit sphere in R3 embedded, and we want to extend it to R3 or R3 with infinity, and then a first question is, which regularity can we hope for? So of course, we cannot hope for having a holomorphic function because it's R3, but then the question goes, what can we do instead? And the second motivation comes from generalizing classic complex dynamics, where we study iterations of holomorphic functions on C, to higher dimensions where we don't have the notion of holomorphicity. And more to the first question again. So we start off with a holomorphic map, and then wherever its derivative doesn't vanish, we know that the differential is kind of like a rotation and a dilation. So an infinitesimal field of circles is pulled back to a field of circles again. And if we weaken this, if we allow some distortion, a very natural class coming up is the class of quasi-regular mappings. So there we have, I probably don't need to define it in the seminar, but I will do it anyway quickly. So we assume to have a continuous orientation preserving map from Rn, from some domain in Rn into Rn again, and we assume it to be a Sobolev map. Then we have this assumption on the differential, so that basically says that infinitesimal circles get pulled back to infinitesimal ellipses where there is a uniform bound on the eccentricity by k that holds for almost every point in our domain. And then if we additionally assume the map to be a homeomorphism, we end up studying closely related quasi-conformal mappings. And for these, there is already quite a large extension theory. So it started off with a result that is not on the slide, but it's due to Berling and Alfors, who showed that one can extend a quasi-symmetry from the line to a quasi-conformal map on the plane. And then similarly, later Alfors showed that if we start off with a quasi-conformal map on R2, then there exists a quasi-conformal map from R3 to itself extending this map. And there was an intermediate step from R3 to R4 by different people independently. And then in 82, it was solved by the classic, very well-known result due to Tukey and Weisela, who showed that if we have a quasi-conformal mapping from Rn to itself, then it can be quantitatively extended to a quasi-conformal mapping from Rn plus 1 to itself that extends the map that we started with. And here, so what we will do later is similar, just that we start off with a holomorphic mapping that is not necessarily injective. There is also a theory of extending quasi-regular functions to higher dimensions, but I just chose to mention this at that point. And now to the second motivating part. If we want to generalize holomorphic dynamics to higher dimensions, we first have to make a choice which mapping that we would like to consider. And for example, we could study holomorphic functions in several complex variables. So in C2, we have both entries would be a holomorphic function, and then we can study iteration of these type of mappings. Or again, we can choose to geometrically generalize the notion of holomorphicity by considering quasi-regular mappings. And one reason for that leads us to to studying quasi-regular mappings is also that if we cling a lot to the conformality that holomorphic functions have outside of critical points, then we end up at Möbius transformations because of Liouville's rigidity result. So yeah, if we don't want to do this, quasi-regular mappings are a natural candidate. But there's one caveat, namely that if we start iterating them, then the constant also gets larger. So an mth iterate of a k quasi-regular map is a priori only k to the m quasi-regular. And for some applications in particular, it would be convenient if the constant does not increase too much. And for that, we like to introduce uniformly quasi-regular maps. So it's the same definition that we had before. The difference is highlighted in red, that the same quasi-regularity constant holds for every iterate that we consider. And it's a very nice class to study. It behaves well, and a lot of classical results from planar complex dynamics can be translated to this class in Rn. But the caveat, so another problem, first I wanted to mention why it is nice that the constant doesn't blow up. So in classical dynamics, a result that is commonly used is Montel's theorem that that holomorphic functions cannot omit too many points without being necessarily constant. And in the case of quasi-regular mappings, Riemann proved that there exists for every k and n, where n is the dimension and k is the quasi-regularity constant, there exists a natural number depending on those two values. And then when the function omits more than q values, it needs to be constant. And so especially if all of the iterates have the same constant, then we can use this result on the family of iterates and prove very nice things. For example, in that case, the classical objects such as the Julia and the Fatou set can be also defined via normality, and we have a lot of the usual properties that we do not obtain, like we strictly do not obtain if we study quasi-regular dynamics. And then, yeah, as Pekka already mentioned, at first it was hard to come up with interesting examples of uniformly quasi-regular mappings that are not injective. That is illustrated, for example, by the fact that they were found by Ibanez and Martin only in 1996, those examples. And for the next part of the talk, I would like to focus on examples arising as extensions. A first nice result in that setting is due to Volker Meyer, who showed that if we start off with a lattice map, I will explain a bit more what that is, then there exists an extension of that lattice map that is uniformly quasi-regular and goes from R3 with infinity to itself. And so a lattice map factors through an automorphism, and in his proof, he did it for lattice maps that arise from the grid that is given by basically z squared, and then the automorphism we consider on C would be just multiplication by a natural number, and then this gives rise to a lattice map. So it factors through with some branched covering map to a mapping on the Riemann sphere to itself. And this resulting mapping is then of degree d squared. That will be relevant a little bit later. That's why I mention it now. But probably the proof methods would also work for different kind of lattice mappings. So in his case, the goal was just to find more examples of UQR maps and not really find them for each degree that we would possibly want, but we might want more degrees, so we can do an argument later on. And a few words on the dynamics of lattice maps. One can show that, or also the reason why they were found, or why people were interested in them in the first place, is that the Julia set is equal to the entire Riemann sphere, and we have a good control of the critical points. Each critical point has a finite forward orbit. And yeah, this will also reappear later because the expanding Thurston maps also have these two properties. Then the dynamics of the resulting map. So that if we view the Riemann sphere as S2 embedded in R3, we can show that 0 and infinity are super attracting fixed points, and their basins are the unit ball for 0 and everything outside for infinity, respectively. And what happens inside is that if we consider a ball of radius r, let's say r is small number, the same happens outside, but I would like to focus on what happens inside the unit ball. So any ball of around 0 of radius r gets mapped to another ball of radius r to the d, where d is the number that we start with and that we consider the lattice map for. Then another example or another set of examples that arise from quite different dynamics is due to Martin from 2004. And he considers rational mappings whose critical points lie in immediate basins of attracting fixed points. And in that case, the mapping, the holomorphic map admits an extension to the upper half space to a uniformly quasi-regular map. And then by reflection, we can obtain a quasi-regular mapping on the entire R3 with infinity. In the same article, he also proved some criteria for non-existence of such extensions. And some examples of those are if we start off with a mapping that has two fixed points that are both two different fixed points that are both attracting, or indifferent means that the derivative is 1 and they have a different rational number as the coordinate. Another criterion is the existence of certain rotation domains. So Siegel disks and Hermann rings are both domains on which the dynamics of the map that we start with is conjugate to a rotation. And the third excluding criterion is that there exists either a super attracting fixed point or a periodic cycle that is super attracting. And in all of these cases, one cannot extend it to a uniformly quasi-regular map on the upper half space. And then if we would we have it on the upper half space, we could reflect. So that just means that we cannot have the same behavior of the unit sphere being invariant, and the unit sphere is of course invariant because it would be the one that has our original map, but the inside and outside components cannot be preserved and in the end being a UQR extension of that. And now more towards the result that I will present later on. An idea is to also prove something for something of that type, so an extension result for rational expanding Thurston maps. And what is kind of a good indication is that lattice maps are an example, but they're a very special example, and the proof also works a lot with the structure that is available for lattice maps in particular, but not general rational Thurston maps. And then it's also this is also not covered by Martin's positive or negative result. And just to recall quickly what a rational expanding Thurston map is, we consider a function from the Riemann sphere to itself, so some rational map of a degree that I will denote by d. It's post-critically finite, so the forward orbit of all the critical points is only a finite set. And the third assumption is expansion. In case we are looking at a holomorphic map, then it's equivalent to there being no periodic critical points. And a more topological way of seeing this was already also mentioned in the previous talk. So that is basically that on the right-hand side, I show some examples. So that is 1 minus 2 divided by z to the 4. And then one can quickly check the assumptions. So we have critical point 0 and infinity. The orbit lands at -1, which is a fixed point and is not a critical point, then what we can observe is that if we look at what the upper and lower half plane do on the backwards iteration, we can see that the size of those sets shrinks, and that is then the topological way of saying what expansion is. So it means that, either the Julia set is this Riemann sphere in the rational case, or the more topological one, that the set of these sizes will go towards 0. Now we know what we are talking about, so I would like to show the result that we found. So if we start off with a rational expanding Thurston map from the Riemann sphere to itself, now there is the assumption that the degree is a square, but that is just for using Folking-Meyer's result, but then one can probably generalize it to drop that assumption as well. And then there exists a uniformly quasi-regular extension to R3 with infinity to itself that is extending F. And now I will explain a bit the proof, and now there is also some acknowledgements to be made. So first, a part of the proof is doing an extension that is in some set that is homeomorphic to an annulus that contains the unit sphere, and then a part of it is basically gluing in a lattice extension due to Meyer near the origin, and then interpolating between those two mappings. And what was done since kind of a long time ago at this point was the part on that contains actually the unit sphere. So where we really precisely approximate the mapping that we start with, and then it wasn't obvious how to continue all the way to 0. And for that, there was, Pekka helped and pointed out a strategy that can be used. So it's a strategy that is very similar to something that Alistair Fletcher and Zhang-Mei Wu do in one of their articles. So that is basically using a nice result that one can interpolate between two quite different mappings that just have the same degree and share some other rather basic assumptions. So now, let's recall a bit to the strategy. So the first part was to prove this really like near the boundary, and for the entire strategy, the idea is to do it inside the unit ball, and then for outside we will reflect. So we reflect along the unit ball, go inside, see what the mapping does, and go outside again. And we subdivide it in those 3 domains where different things happen. The first one I denoted here by omega, and in the picture it will be bounded by kind of this first sphere that doesn't quite look round, but then it will result in something homeomorphic to an annulus, and it's the outer boundary will be the unit sphere. Then a second part of the domain that I here point 3 is a ball of some radius that is small enough that it's not near this domain where we have to be precise. And then the third domain is everything is basically the rest, where we have to interpolate between those two different mappings. Here is just again what I said, that what we do on which part. Let's now dive into the approximating precisely part. So there the idea is, I already mentioned that Folking-Meyer's extension has the property that spheres get mapped to spheres of radius r to the d. And here the idea is to define sets that are homeomorphic to spheres with a radius that is dependent on the dynamics of the mapping that we start with. So we kind of want to have a radius at a point z that says, okay, the distance of the point where we want it to be for an nth approximating sphere is similar to the derivative. And one can also show that, so if we go back to the Thurston maps, if we look at this picture, if we would go into one of these tiles and just pick some nice base point that would be in the interior, then this derivative would also be approximately similar to the size of this tile. So it's basically how much we get shrunk is kind of the distance towards to the unit sphere intuitively. And of course, at critical points, this definition cannot work. So we have to find a way for the derivative not to diverge or not to be zero. And that is the main technicality of this whole problem, and I will get into it a little bit later. But then once we have this definition of a radius, then we do kind of a similar mapping, that spheres get mapped to spheres and they go closer to the unit ball. So as n grows, it is also due to expansion, basically, that the value of Rn will be close to 1. And let's see what we do near the critical points. First, we make a simplifying assumption that each critical point is mapped to a post-critical point P that is then a fixed point. We can then, because it's a fixed point, it has a linearization. And if we iterate backwards, so if we start off with a small, nice enough neighborhood around the post-critical point, we obtain a sequence of sets that shrink towards that point. And on each of those sets, it's the dynamics will be conjugate to just expanding by the derivative. Then, of course, all of these sets all have a pre-image of around a critical point. And here with the shading, I indicated the branching. And this whole map can be conjugate just to z to the power of d. And then the idea is to, down in the unit disk, we replace the dynamics of z to the d by the winding map. So there we map r times e to the I theta to r times e to the I d theta. So in the angle direction, we still do basically z to the d, but not in the radial one. And what happens then is that we lose holomorphicity, but on the boundary, the derivative will also be equal to what we started with. And we still have locally, if we restrict and we are not at the origin, then it's still kind of locally a bi-Lipschitz map. So it's still nice, but not holomorphic anymore. And in that case, so here is just a small repetition. And then with these neighborhoods that I mentioned before that are shrinking towards first the post-critical point, and then we look at the pre-images around the critical point, we will only modify the map on those shrinking neighborhoods. So for large n, this neighborhood will become small, since we iterated first near the post-critical point where they have to get small, and then so because of that, on most of the Riemann sphere, the mapping will be exactly the one we started with, but just near the critical points on smaller and smaller neighborhoods, we do this modification. And then each function fn has a non-vanishing derivative everywhere, and we can still show that it converges to the map that we started with. And if we take out the critical points, it's still locally by Lipschitz. Then now the idea is to replace the iteration. So we replace f to the n by the composition of all of these maps. And what happens there is that, so if we start off with a point that is not contained in any of those critical neighborhoods or not in the basically nth critical neighborhood, then its forward orbit under this composition will be exactly the same as the iteration of the map that we start with. But if we start off with a point that is close to the critical point, then it will be modified once. But then, since it was close, we know its dynamics near the post-critical point very well, and it will stay close enough for long enough that we can guarantee that this by Lipschitz modification happens only once for that point. So one could also worry, so if one changes a function and then iterates it, one also has to worry about distortion accumulating, but here it will not accumulate because it just only happens once. So that was how we fixed the issue of the vanishing derivatives. And now we got this working definition of a local radius. And then we set what we call approximating spheres to be parametrized in a very simple way by just, okay, we take the point Z and then we project it down to this Rn of Z. And then it gives us kind of a natural definition on those spheres. So on the nth approximating sphere, we define an extension by taking a point Z and Rn of Z. And then we look at where the mapping should take it, and we step down one sphere. So we go and look at the radius Rn minus 1 at the point f of Z in the sphere. And then for everything in between, we will just interpolate between the values that those two spheres would give us and then extend it to everything. Now we can understand, so from this definition on the spheres, we can understand what our domain and what the target will be. So if we can have a point that is always lying between one where this sphere map is defined and the next one, basically, then we know how to define it. But once we end up at points between the first one and the second one, it's not obvious how to continue. And it's not obvious how to continue this definition and have 0 as a super attracting fixed point. But at that point, we will start interpolating and glue in the lattice map extension by Folkenmayer. And now also a word about the branch set. So the branch set of the map that we start with were those critical points, and so it will look like for our map, like just basically straight lines that are rays that would connect the critical point towards 0, and then it starts at some critical point and goes just all the way until our extension is defined in that way. Here is this is some simulation for a real function. It's a bit difficult to see what exactly is going on, and what I did here was I cut off the 0. So 0 is cut off by putting in the winding map, but here I just did it manually. So those parts that look very round would probably not look as round because it was just an ad hoc manual solution. But what we see here is that there is basically a first sphere lying in a second and so on. And in the second one, there's a bit more going on, and there are a bit, I plotted the first one to the fourth one. And a few, maybe one word about why we can obtain uniform quasi-regularity. We can, whenever we are in this domain, we will restrict to points that are separated by two adjacent spheres, and then we look at what the mapping does in the spherical as well as in the radial direction. And by the definition of what the local radii are, we can conclude that it stretches along there by the value of the derivative at the boundary, and it does the same thing in the spherical direction. In the spherical direction, we we are using Kirby's distortion theorem, and that is also in particular not dependent on the iterate, and that is then why we get a uniform quasi-regularity, because the constants come from results that do not depend on the iterate, basically. And once we go through such a critical point, we know, as I mentioned before, that it happens only once. Then, yeah, this is not so relevant at this point. And now, yeah, we've done it at this part where we need to be very precise. And this is again to outline what happens in the rest. So on a unit, on some small unit ball that is here indicated in kind of in pink, we will consider Myers-Lattice map extension, which maps the R to the ball of radius R to the ball of radius R to the D. And then, yeah, zero, everything just gets absorbed towards zero. And in between those domains, we have kind of two mappings given. So the first one is given from our extension that comes from the original function. So we a natural candidate would be to have this map on the first approximating sphere to the constant one, to just take again the mapping that we start with and then map the radius constantly. And we also have a mapping given on the second boundary where we need to interpolate, that is given by Myers-Lattice map. And then there is a very powerful result due to Bergstein and Edmonds, and I don't expect anyone to understand. This result is really like a bit of a mouthful. So what one just has to, the important thing is that we have two kind of boundary maps, and then the conditions are very mild. They just need to be kind of PL covering maps on, they both need to be orientation preserving piecewise linear branched coverings of the same degree. And then under some assumptions on the target space, there exists an extension. So there exists then a piecewise linear branched covering that that extends to everything that is bounded between those two. So it will extend to the annulus here that is bounded between S0 and S1. And also this, there we have less control of the constants, but this will only happen once along an orbit of a point. So this is not a problem for uniformity of the constants. And this was all that I wanted to say about the extension so far. And if you have questions about this, you can also ask now, or we can ask later. And I would move on to the second part about hyperbolic geometry and hyperbolic applications of this. But yeah, okay. So now the idea is to equip the unit ball with the Poincare metric. So we look at it through hyperbolic eyes. And whenever we study, so yeah, a nice class of mappings in hyperbolic geometry are quasi-isometries. I repeat the definition quickly. So they are by Lipschitz mappings with a constant error. And now we only look at the part, this domain omega, where we did kind of our construction, and we don't take the inside into account where we glue in Folke-Meyer's map. So it's only about the first part of the extension. And we can show that if we equip everything with the hyperbolic metric, that if we restrict to small sets that are not in the branch set, so we assume that the map is locally injective and we still have to restrict to slightly smaller sets, then our extension is locally a quasi-isometric embedding, and the constants are also quite good. So we basically have a rough quasi-isometry resulting if we look at it with the hyperbolic metric. And just for intuition, let's go back to this picture quickly. So a way of seeing this is that if we look at those sets, that they are about the size that they are away from the diameter, and the same happens for the image and the second forward image. And then this basically translates to the mapping being a quasi-isometric embedding with good control on the constants. Now, the part about Sullivan's dictionary. So, yeah, Sullivan's dictionary was also mentioned already in the talk before, and it is basically the philosophy that the theory of Kleinian groups and the rational mappings on the Riemann sphere are related. And on the left-hand side, we study discrete subgroups of Möbius transformations in three-dimensional hyperbolic space, and yeah, they are the isometries of three-dimensional hyperbolic space. And then on the right-hand side, in the rational dynamics world, we study rational mappings on the Riemann sphere, and their Möbius transformations also play a role as the automorphisms. What you see in the two images, just like I don't know, like for illustrations, are a limit set of a Kleinian group, and on the right-hand side it's a Julia set. Then one part from the Kleinian group world would be the Cannon-Thurston map. There one can start off with a hyperbolic 3 manifold that fibers over the circle. That means that the manifold can be obtained as a product of a 2-dimensional hyperbolic surface times 0, 1, and then modulo an equivalence relation. The equivalence relation is induced by saying that the point x and 0 is equivalent to phi of x at height 1, where phi is a pseudo-Anosov map. And if we construct a 3-dimensional object from a 2-dimensional one, we can also ask how does that affect the universal covering and the fundamental groups. And here I denoted the universal covering with those tilde. So the question is basically how does the universal covering of the 2-dimensional manifold sit in the 3-dimensional one? And we can model them as the unit ball in the plane, so as the unit disk for the sphere, for the surface, and respectively the unit ball with the hyperbolic metric for the manifold M. And it turns out that under this inclusion, it can be extended to a mapping on the boundary. So the circle S1 is mapped continuously into the cover of the manifold, and it traces out a space-filling curve on the sphere. On the right-hand side, there's some image that is in one of Thurston's papers about this. So it's kind of showing how this surface or how this embedding becomes quite wild in the boundary. And then on the right-hand side, our goal is now to find an explicit immersion of the hyperbolic plane into the unit ball, such that an F-invariant space-filling curve is traced out. And I will show soon what it means to be F-invariant. And here also F is again a Thurston map. Then, so the more precise statement is that if we start off with a sufficiently high iterate of a rational expanding Thurston map, then we can find an immersion of the hyperbolic plane that we view at, or we can also view it as the disk, into 3-dimensional hyperbolic space, and a sequence of curves where each curve lies in one of those approximating spheres that we have defined before, that converge to a F-invariant piano curve that lives in this surface. So this curve will then live in S2, or identified with the Riemann sphere. And this immersed surface cannot be quasi-isometric to the hyperbolic plane. That is just because the boundary makes it impossible. One result that we use for this, and also what it means to be invariant under the Thurston map, is due to Daniel. He showed that if we have a sufficiently high iterate of an expanding Thurston map, then there exists a space-filling curve, so parametrization, a map from S1 to the entire Riemann sphere, and then the diagram that I showed in the bottom commutes. So we have this map to the Riemann sphere, and then down there we can apply the Thurston map that we were starting off with, and then in this diagram, maybe what we can view as complicated. So maybe this Thurston map is a bit of a complicated object, but then once we know the space-filling curve, the map becomes very simple, and it's like z to the power of d, where d is the degree of the mapping. And further, in the proof, there is also a sequence of curves that will then converge to this limiting space-filling curve. The first one, so one starts off with a curve containing the post-critical points, and then one deforms it so that it basically covers the whole pre-image of that curve, and that is kind of shown on the left-hand side. So we start off with this curve gamma 0, and then we go back, and then and we can also, alternatively to taking a pre-image, one can deform it via some homotopy. Then the idea is to do something similar as in this picture on the right-hand side. So we have curves and homotopies, and we will embed each stage of the curve into an approximating sphere, and then make the time parameter of the curve become the way parameter, telling us how far we are from one to the next. And that basically means is that we do something similar to the picture on the left-hand side, where at each where the curve is developed over time, and here also over space, and then on the right-hand side, in the first approximating sphere, there would be a first approximation of the curve, and then this whole surface would trace out kind of an immersed plane that will then have the F invariant space-filling curve as the limiting object. And now, since we are on the domain of our extension, we can ask what happens if we apply the extension to it. And both constructions are done in a way that if we are away from the critical points and also pre-images of critical points, then we can apply the extension, and we end up again in that plane that is traced out. And if we are too close to the critical points, then we might not end up in the plane again, but the distances are uniformly controlled to what we started with. So this is all I wanted to say today. And yeah, thank you very much for your attention. And I'm also happy to answer questions. I was a bit quicker than I needed, I'm sorry.
Yeah, well, okay, let's thank Julia, and let me open the discussion. So are there comments and questions?
Yeah, thanks, Julia. I was actually thinking, I started to think during the talk, in your construction, what you had in the beginning, so that you have the Thurston map on this Riemann sphere, expanding Thurston map. So there's a kind of natural metric, kind of intrinsic metric there coming from the visual metric. But then when you do this kind of extension to the both directions, then we don't have any more kind of this expansion feature because you have a contraction to the origin and to the infinity. So I was kind of wondering, so that have you perhaps been considering that, is there any kind of codimension one visual metric theory for this type of mappings, which would kind of give a kind of interesting metric characterizations for these extensions?
Yeah, so in the process, I've tried to kind of use the visual metric on the surfaces, but then yeah, at the point I was I don't know, I wasn't really getting anywhere with what to do in this third direction. No, that
Yeah,
doesn't.
because it's somehow different from the
Yeah.
kind of the direction of the original dynamic. So that's why I kind of, yeah, that's very interesting. I just find it somehow appealing question. That's why I was. This was perhaps came from out of blue. So that's sorry
No,
about that. Sorry about that. Yeah.
Well,
Funny enough, because I also started thinking about things during that talk. So you got it to the entire S3 with Pekka's comment. Yeah. Okay. So you need the assumption d squared. Is this because you're using Volcker's map? You're using the kinds of maps that Volcker constructed, and you need d squared because those are the maps that you know that would keep like one half of the S3 on the same half and the other half on the same half, but are still UQR. Is that like the reason?
So yeah, the reason is just that one would need to adapt his proof, but probably so he only considers the type of lattice maps that arise as that are basically coming from the integer grid and then stretching by an integer, but one could just pick a different grid and then obtain different degrees. So we also think that one can obtain the degree d, and his proof method doesn't really imply that the d squared needs to be there. Now it's just there for the sake because this is like really fixed, and the other part is we would have to slightly generalize Folkenmeyer's result in order to have degree d.
I mean, I guess we're really sure that we can get. I mean, there's also somehow the assumptions d has to be at least 3 in this Edmonds.
This one we cannot get rid of.
Yeah.
Yes, the degree should be at least
this we
3.
don't really know, but I think every other degree we can get, but we only kind of discussed it last Tuesday, and like I guess like sometimes you have to check that.
So you suspect that you can get rid of that d squared?
Yes,
Because
I mean, I'm actually 99% sure.
Yeah, because I started wondering the opposite, because there's a result by me and Pekka, which tells that when you have UQR maps on a manifold which has like non-trivial cohomology, on a manifold which has non-trivial cohomology, then you suddenly get obstructions for what the degree can be, and you get exactly these kinds of exponent things. So I wondered if, like, you're in a weird situation where you're mapping fixes and S2. So I wondered if anything like this could produce anything similar, but at least briefly checking, I'm not finding a 2 cohomology class anywhere. Like apparently the relative cohomology of S3 relative to S2 vanishes in degree 2, so nothing useful there. So might be that you are indeed right.
Okay, do we have any other questions?
Yulia, yeah, can you also elaborate a little bit on this connection that you mentioned with the Cannon-Thurston map, this kind of space filling surface a little bit more? Thank you.
Yeah, so what would you like to know?
You mentioned some kind of non-quasi-isometric, non-quasi-isometry from the space. Yeah,
yes.
that slide.
Yeah, that one I skipped through quickly. So yeah, we were saying that we have this nice parametrization that is coming from the isotopies, and then it's a result by Mario and Schramm, who classified basically what can be a quasi-isometric image of a hyperbolic plane. And there, the boundary really needs to be a quasi-circle. So that is kind of a very immediate obstruction to this being nicely parametrized ever, or nice in the sense of a quasi-isometry.
Okay, thank you.
I mean, I guess, to some extent, I think, and I think it's actually not known that in the group case. I mean, it's sort of interesting because you embed a hyperbolic plane into a hyperbolic three space, and your first idea is like, okay, you just have an equatorial plane, but it's exactly not how it's embedded, because it's embedded in such a way that when you go to the boundary, like the two sphere, you got this the space filling curve. And I think it's not really known. I mean, so it has to violate, the quasi isometry. And the question is, how much does it violate that? And I think that's actually not known, but you can also ask this in this setting where you also have an hyperbolic plane embedded, and sort of, between these sort of, in these sort of annuli, you have this homotopy that sort of make the curve more and more complicated till at the boundary you get the space filling curve. And then you can ask, like, okay, how much does this hyperbolic plane violate to be quasi-isometric to the hyperbolic plane? And in a sense, we don't know, but I think this is much more traceable than in the group case, because I think in a sense, like, it's a kind of explicit, constructed, and you can sort of ask how much does it violate the quasi-isometry?
Yeah. We also did a similar construction that has then a much more tame result in the sense. So we can also use exactly the same strategy and to have the curves approach one that is a quasi-circle and that is an invariant curve. So that's also that is motivated basically by a result due to Mario and Daniel, where they show that a Thurston map has an invariant curve, and then the motivation there is maybe a little bit different. But then if we do kind of this plane, then it becomes quasi-isometric to the hyperbolic plane, and it's also not so surprising that one can obtain something that is kind of dynamically relevant. So tracing out a curve that is invariant under the map that we start with, and obtaining a nice embedding in the sense that it's a quasi-isometry.
Okay, so other comments or questions?
Yulia, yeah, I have maybe two more questions. So one of them, I just wanted to clarify what you just discussed previously. So you're saying that you hope to get rid of these d squared assumptions on the degree, but
Yes.
the question is, okay, does it still have to be a composite number, or you could also cover prime numbers?
No, prime numbers would be fine.
Prime numbers will be fine. Okay.
So the point is just that if we start with a different grid from the lattice map, basically the proof of Holomorphic, what he does is that he in the planar case we say that we have this branched covering map that takes one square of the pillow and maps to the upper and lower half plane, and then he has an analogon for this basically on some beam. So we can imagine maybe like a square times r, and this is then mapped to the upper half plane, and then any adjacent thing in that grid that will be the lattice map grid will be mapped to the lower half plane. And this can be done not only for square maps and square grids, of course, but then one just has to write down this. Does it make sense?
Yeah, okay. And okay, so and the second question was concerning, so you had you had some result on the slides which was saying that if you have let's say a periodical critical point, you could not get an extension to the hyperbolic free space, but what about just kind of not kind of this symmetric extension, but like extension to, well, like, I mean, to the three-dimensional space. I mean, not just to the kind of to the hyperbolic free spaces.
Yeah, this is a good question. So I've read the proof of that, but I think it really uses that he would aim for the upper half plane, and I think it doesn't immediately translate to if we aim for the entire space. So I'm not sure about that about that question, whether it would be possible.
Yeah,
But
okay.
I think it's also a direction to keep exploring. So one thing that I also wanted to do at some point is to ask if one can admit maybe some periodic critical points, or if one can admit Fatou components in a similar construction.